Okay, in this video I'm going to talk about entropy and spontaneity. So entropy is a measure of the disorder of molecules. The absolute entropy values exist for different substances, and generally speaking, the state of the substance gives an indication as to the absolute entropy. If a substance is a solid, it will tend to be quite ordered and will have therefore a quite low entropy value, and if something is a gas, it will be quite disordered and will tend to have a high entropy value. It is possible to find the entropy change in a reaction by subtracting the total entropy of the reagents from the total entropy of the products. So for example, if we have the reaction of methane with oxygen to make carbon dioxide and water, we can find the absolute entropy values for each of these substances in the data booklet. So methane is a gas and has an absolute entropy of 186 joules per Kelvin per mole. Oxygen is also a gas and will have a total entropy of 161 joules per Kelvin per mole. Carbon dioxide, which is also a gas, will have an absolute entropy of 213.8 joules per Kelvin per mole. And water is a liquid in its standard state and will therefore have an entropy of only 70 joules per Kelvin per mole. So these are all positive values. The lowest possible entropy is 0 because to have an entropy of 0, you have a perfectly ordered crystal lattice where none of the particles are moving. It's not possible to have a lower entropy than that, to be more ordered than that. So it's impossible to have an absolute entropy which is negative. However, it is possible to have a negative entropy change if the overall entropy in the reaction is decreasing. Now the first thing we need to do is we do need to take into account the coefficients. So we have 2 oxygen molecules, so we must multiply the entropy of the oxygen by 2, and we have 2 water molecules, so we must multiply the entropy of the water by 2. And entropy is denoted by the symbol S, so the entropy change in this reaction is going to be the entropy of our products, so 213.8 plus 2 times 70 minus the entropy of our reagents, so 186 plus 2 times 161, which gives us an overall entropy change of minus 154.2 joules per Kelvin per mole. So notice that we can have a negative entropy change in the reaction, and this makes sense. On the left-hand side here, we have 3 molecules of gas, 1 molecule of methane, 2 molecules of oxygen. On the right-hand side, we've only got 1 molecule of gas, 1 molecule of carbon dioxide, and then 2 molecules of liquid for the water. So overall, our substances have become more ordered over the course of this reaction, as we now have less molecules of gas present. So we have an overall negative entropy change. So the entropy indicates the change in disorder or order or disorder of our system. Normally we use the entropy to help us to determine the spontaneity along with the enthalpy change that we've found out how to find before. So we have a term called the Gibbs free energy, which is denoted by delta G. And the Gibbs free energy is a measure of the energy which is available from a reaction which is able to do useful work. And we can find the Gibbs free energy in 2 ways. We can either use the Gibbs free energies of formation of our products minus the Gibbs free energies of formation of our reagents, in very similar to what we did up here with the delta S, and we can therefore find the overall Gibbs free energy change of the reaction. Or, so that would be delta G equals delta G of formation of the products minus the delta G of formation of the reagents. So that allows us to find the overall Gibbs free energy change of the reaction. But more commonly, we find the delta G from the enthalpy change of the reaction and the entropy change of the reaction, along with temperature we need to take into account the temperature of the reaction. So the Gibbs free energy change is equal to the enthalpy change of the reaction minus temperature times the entropy change of the reaction. Now, one thing that we have to be very careful of is the units. The units of the enthalpy change of reaction delta H are in kilojoules per mole, or they're usually in kilojoules per mole. The units for temperature are in Kelvin. They must be in Kelvin, it must be absolute. And the units for entropy change are normally in joules per Kelvin per mole. Now, we have a problem here because we have two different units for energy. We have kilojoules and we have joules. So it is absolutely essential that the value for the entropy is converted into kilojoules before we do this calculation to find the delta G. And if we do that, we can then find a value for the delta G, which is going to be in kilojoules per mole. With our temperature cancelling out. Now, a way of visualizing how this works is if you imagine a graph here where the x-axis is the temperature in Kelvin, starting at the origin, so 0 Kelvin is the lowest possible temperature, and on our y-axis we have the delta G, running from positive to negative. Now, at 0 temperature, at 0 Kelvin, T delta S is 0, since T is 0. Therefore, the delta G will equal the delta H. So if we start with an endothermic reaction, the positive delta H, we're going to be starting with a positive delta G, where delta G equals delta H. Now, there are two possible directions that this point can go as we increase the temperature, depending on whether delta S is positive or negative. If delta S is negative, and we are subtracting T delta S, so minus T and then minus delta S would give us a positive gradient on this line if delta S was positive. So as the temperature increases, T delta S becomes more significant, and we are subtracting a larger and larger negative value, and therefore our delta G is becoming more and more positive. If our delta S was positive, our line would slope downwards. Because here we are subtracting a positive value, so we're starting out with delta G equaling delta H, but then as we are subtracting a larger and larger T delta S value, our line slopes downwards. And at a certain point here, where the line passes through the x-axis, at this point T delta S is now greater than delta H, and we are now going to have a value of delta G which passes from positive to negative. At this point, the reaction would become spontaneous. A positive delta G is a non-spontaneous process. So a positive delta G means the reaction that will not happen. If you have an endothermic reaction which is becoming more ordered, no matter what the temperature is, it will never be spontaneous. It's always going to have a positive delta G value. However, if you have an endothermic reaction which is becoming more disordered, once the temperature becomes high enough, then the reaction will become spontaneous as your delta G becomes negative. And that happens, that point is when delta G passes through 0. Now we can also do the same thing if we have an exothermic reaction with a negative delta H, and again we can have the same two lines. So if we have a negative value for delta S, we start out with a negative delta H, we subtract a negative T delta S, and at a certain point the temperature is going to be high enough that T delta S is greater than delta H, and therefore our delta G is going to pass through 0 and become positive, and the reaction will stop being spontaneous. If we have a positive delta S, then we are subtracting a positive value, so we have a negative delta H and we're subtracting a positive delta S, and no matter what the size of T, we are always going to be making delta G bigger and bigger and bigger, and so our line is going to slope downwards, and this reaction will always be spontaneous. So a negative value for delta G means the reaction is spontaneous. A positive value means it's non-spontaneous. In this case here, An exothermic reaction which is becoming more disordered with a positive delta S is becoming more and more spontaneous. An exothermic reaction which is becoming more ordered will pass a point at a certain temperature where the reaction is no longer spontaneous when delta G passes through 0, and therefore it stops being spontaneous at that point. So, in summary, delta G is a measure of spontaneity. In order for a reaction to be spontaneous, delta G must be negative, and we can determine delta G from the enthalpy change delta H and the entropy change delta S, taking into account the absolute temperature. In order to determine which is more significant, we need to compare the magnitude of delta H and the magnitude of T delta S. If T delta S is greater, then the entropy of the reaction is going to be the determining factor. If delta H is greater, then the enthalpy change of the reaction is going to be the determining factor. So there we have entropy and spontaneity.